Let's now do an example involving collision, angular momentum conservation, and perhaps other topics. Okay, here's the setup. So before the collision, let me just set it up like this. A pencil, this is a pencil, or a uniform bar. It's falling downward, okay? With speed Vg equals, let's say, minus 5j in meters per second, okay? Moving fast. And then the collision itself I'm just going to picture it. So the collision happens, let's say, at some point that is, let's say this length is L. Okay, it happens at this is L over 4. Okay, so imagine someone dropping their pencil from some height, and the pencil is moving downward, and then eventually has a velocity minus 5 meters per second, sort of downward. And then you stick your finger out, and the pencil hits the finger. So what happens? So there's a collision between your finger. You can imagine your finger sticking out of the plane of the board or the plane of this page, right? So your finger is sticking out, the pencil is falling down. It hits the finger or hits, let's say, the edge of a table or something like that. And then what happens? Usually the pencil will start rotating about this point. It'll have purely linear velocity falling down, and then it will hit it and then rotate about that point in some manner. You can try this at home. Maybe I'll shoot a video of pencil falling and hitting my finger and rolling off of it. In any case, so that's the collision. This is some point P, and then after collision, so P is some fixed point, fixed pivot. After collision, the pencil rotates about pivot P without slip. Okay, so this is the situation before the collision, this is the situation after the collision. Let's give the post-collision velocity state some notation. So we have some point P. So we are imagining it's a thin pencil, so it's got no width. Even though I've drawn it with some width here, the point P has is basically, you can imagine it to be at the center of this bar or something like that. There is no width here, even though I've drawn it like that. Maybe it's better to put P right in the middle. In any case, imagine now that it has some angular velocity omega k. I've drawn it omega k with this sign convention, the anti-clockwise sign convention, which is the standard thing that we use in this course. Now, of course, you can sort of feel intuitively that if it is falling and hits this point and pivots about this point, it's going to have a clockwise angular velocity or angular momentum. But this is just sign convention. We will eventually find, hopefully, that the resulting angular velocity is actually negative, which will agree with our intuition. Okay, so but that's the setup of the problem. So the question is find omega after the collision. Okay, find omega after the collision. So what principles can we use? Can we use linear momentum? Can we use angular momentum? So what we are saying is the fixed pivot note pivot P is fixed and cannot move. Its mass is not known, or essentially it could be thought of as having infinite mass because it does not. It's stated to state that it cannot move, right? So effectively infinite. Okay, so that's an aside. Okay, so what principles can we use? All we have is this bar. We're not really going to consider the pivot at all, because all we've been told is that the pivot cannot move. So what principle applies to the bar? So let's draw a free body diagram of the bar during the collision. So before collision, first of all, SBD. So it's convenient to sort of think about these things in terms of FBD still. So all you have is mg downward. That's before the collision. During the collision, what do you have? We have the bar, we have mg, and then at point P, so that's mg is acting at point G, and then at point P, there's this huge force. Okay, this is the collision force, or the force of interaction between the point P, the pivot P, and the bar. And this force produces a finite change in velocity of the uniform bar in infinitesimal time. So whenever you're asked to do a problem like this and it's not stated that it happens over infinitesimal time, say assume collision happens, because this is going to be a common assumption that you will need to make unless otherwise stated. Okay, collision happens in infinitesimal time. So during the collision force is basically infinity. Okay, it's an infinite force. So there's a finite force mg and there's an infinite force due to the pivot on the bar. So we cannot really apply linear momentum balance, or at least the linear momentum balance has the right hand side. The impulse is not equal to 0, right? So what can we use? It turns out we can use angular momentum balance about point P. About point P, if you take angular momentum about point P, the only infinite moment is due to this collision force, but that's going to be zero about this point. And there's a finite force which has a moment about point P, but that finite force or finite moment integrated over a very short period of time has no moment, right? So let's take moments. So let me say it differently. Angular momentum is conserved about point P. Of bar conserved about point P because the infinite force acts through P and has no moment about P. Mg is a force, has a finite moment, finite meaning not infinite, about P, but when integrated over infinitesimal duration, it's got essentially a zero impulse. Okay, so the only big force is zero moment. The only small force doesn't matter because we're taking the collision duration is infinitesimal. So we ignore finite forces in collisions, basically. Okay, so what we're going to say is angular momentum before of bar of pencil before collision equals angular momentum after collision. We use the notation H. So just to be clear, this is about point P. It's only true about point P. Okay, so we're going to say H, the angular momentum about point P initial equals H about point P final. What is H about point P initial? So angular momentum is defined as, if you recall your previous video, it's I omega plus R cross mv. Okay, so it's basically Ig omega initial K plus R G with respect to P cross mv G initial. Okay. So that's this thing. This is equal to 0 because we said it's not rotating initially, plus Rg with respect to P is P is L by 4 here, so G with respect to P is L by 4 times I. Okay. So this is I, this is J. L by 4I crossed with M. Let's just leave it as M. I've not given you what M is, but we will see that it will drop out of the calculations. VGI, I think I said, was minus 4 meters per second. Okay. In the J direction. So we are going to get ml by 4 times minus 4, which gets cancelled. I cross j is k, so we're going to get minus ml k. Okay. This is in some weird units, but we're not going to worry about it. Okay. Maybe we should have substituted Vg later on, but we'll just leave it as it is for now. What is the final angular velocity? Okay, so, oops. The final angular momentum is, you can write it a few different ways. It's going to be equal to Ig omega final k plus R G with respect to P cross M Vg final. So let's just use this formula. You can also use, it turns out, let's sort of do this in two different ways if you want, and you'll get the same answer. So let's do it two different ways. Let's call this method 1, method 2. So if the point P on the rigid body about which you're taking moments is actually fixed, it's actually equal to IP omega F K. You can also do that. In any case, if we continue with this process, what we have is equal to IG for uniform bar is M L square divided by 12. This should have been without the vector because we have the unit vector here. So that's omega F K. And then RG with respect to P is still L over 4I crossed with M. What is VGF? If you have this bar rotate about this point with angular velocity omega, Vg is going to be, this point is going to be L over 4 times omega in the upward direction, right? So that's what that's going to be. That's because of the no slip sort of condition. And we can expand that out to get M L square by 12 omega F K plus I cross J is K. So K M L square 4 times 4 is 16. And omega F, same thing. And we get ml square omega F 1 over 12 plus